Here I'm working with a titration of my weak acid, acetic acid, just like in our previous example. It's getting neutralized by sodium hydroxide. The concentrations and volumes are given: 50 mils of 0.120 molar acetic acid, 0.240 molar sodium hydroxide. And we have three different scenarios. In one of them is before we reach our equivalent point. Once we reach our equivalent point, that will be case B, and then right after. We want to figure out what is the pH in each one of these cases. The first thing we need to know is the chemical equation for this process. We have it right here. We have our acetic acid being neutralized by our hydroxide anions, giving me my acetate ion, and then water, which doesn't really count for our equilibrium. We want to compare moles to moles. That's the only way you can compare how many you are getting neutralized. According to the stoichiometric factor we have in this chemical equation, for every 1 mole of acetic acid that I have, I'll need 1 mole of hydroxide anions to neutralize them. So my first step is going to be calculating how many moles I have at the very beginning, my acetic acid. So I have my volume, I change it to liters, my molarity, which is moles per liter, is at 0.12. That gives me 6 times 10 to the minus 3 moles of acetic acid, or 6 millimoles of acetic acid. In my first case, I have 10 milliliters of my base. I have a concentration, so I calculate how many moles of my sodium hydroxide I've added. Turns out it's 2.4 times 10 to the minus 3 moles. I will subtract from the amount of acetic acid the number of moles of the sodium hydroxide that I added. That'll give me 6 times 10 to the minus 3 minus 2.4 times 10 to the minus 3, these two numbers right here, and that'll yield 3.6 times 10 to the minus 3 moles of my acetic acid. Now, what is happening at the same time is that for every one of my acetic acids that I neutralize, I form one of my acetates. So now I have a ratio between my weak acid and my conjugated base, so I can use Henderson-Hasselbalch to determine the pH of that system. I find the pKa, which if I have the Ka, which I do have, I can just convert, and then the logarithm of the ratio. That'll give me a pH of 4.56. Now in my second case, I've added 25 mils of sodium hydroxide, or 0.025 liters. That'll give me 6 times 10 to the minus 3 moles of sodium hydroxide. That's exactly the same amount of moles of acetic acid that I have, so that means that I've completely neutralized both species, so I've reached what we call the equivalence point. So now we gotta look at our acetate ion, which we should have this same amount, 6 times 10 to the minus 3, and the reaction should be going in the reverse order. Our acetate should start reprotonating into acetic acid and then our OH. So we're gonna need, you guessed it, a nice table. First, we need to figure out what is the total volume of my system, because by now I've added quite a bit of my base. So I've added 25 mils plus the initial 50 milliliters that I started off with, giving me a grand total of 75 milliliters of solution. So I will need this volume to calculate the concentration of my acetate ion, which is moles per liter, or 0.08 molar solution. So my reaction is reversed. I'm no longer using Ka. I'm now going to be using my Kb constant, the base dissociation constant of that conjugated base, which we have to be 5.6 times 10 to the minus 10. So this is my reaction as it's happening. I start off with the calculated concentration. These two neutralize each other, so there's nothing there. My acetate is getting reduced. My hydroxide and my acid are getting increased or added, and then these are the amounts in equilibrium. I can do the same simplifications that I did for my Ka, leaving me with this right here at the bottom. X squared over 0.08 equals 5.6 times 10 to the minus 10, meaning that my X equals 6.7 times 10 to the minus 6 molar. From there, I calculate my pOH minus the logarithm of my concentration of hydroxides, and that computes to 5.17. I can now calculate my pH by remembering that pH plus pOH equals 14, or in other words, 14 minus my pOH equals my pH. And that's what it is right here at the bottom, the very bottom. 14 minus that 5.17 gives me a pH of 8.83. And that's pretty much what happens at the equivalence point. My last scenario, I've added 35 mils of NaOH, so I have 10 milliliters in excess. And there's two ways that we can work it. I'm going to take the long route, and then I'm going to show you how to do the short route. First, I need to figure out what is the concentration of acetate ion at this point. It's 0.07 molar. I added 10 more mils, so I have 50 plus 35 milliliters. I have 85 milliliters of solution in total. I have it right here, the moles over the liters. And I repeat for my hydroxide. At this point, I shouldn't have, initially, any acetate ion, which I don't. I complete my ice table. I end up with my equilibrium concentrations right here, as you can see, 0.07 minus X, and 0.028 plus X, respectively. I work those variables into my Kb expression. You have it right here. And again, we're going to simplify our expression. 0.028 plus X is about 0.028. 0.07 minus X is about 0.07. Putting all of that into my Kb expression yields a value of X of 1.4 times 10 to the minus 9. This number, when put into our expression for our hydroxide, 0.028 plus 1.4 times 10 to the minus 9, that number is so small that it remains virtually unchanged. That means that if I had noticed that I can simplify here, I could have just skipped over to this step. My pOH, and then for my pOH, 14 minus that number will give me the pH, which in this case is 12.45. And that's pretty much how you calculate pH at the very beginning of our titration, at the equivalence point, and much after.